Hello everyone, this is the problem solving session for the NPTEL course Advanced Robotics for week 3. And in the previous week what we had covered was DH parameters, right? How do we assign frames to the robot, right? And specifically we assign frames to the joints of the robots, right? And then we discussed the DH convention of how we actually assign these frames. Then we moved on to the discussion of parameters, right? So there were 4 parameters in total: link length, link joint angle, joint offset or the frame offset that is represented by D, and the twist, right? Twist angle. So like what is the angle that the two joint axes make with respect to each other along the common normal, right, that passes through all of them. So we had discussed this, and what we discussed after that was why do we do this, right? Why do we define these GH parameters? So we discussed that we can get the transformation of different frames, and then we can get relative transformations between any two frames, right? Not just from, let's say, the end effector frame to the ground frame, right? So if we, let's say, this is the inertial frame, right, and there is some robot, right? Maybe like this, right? Some robot, and this is the, let's say, end effector frame, right? Let's mark this as cap italicized E subscript small e, right? And this is our origin, and this is our inertial frame, right? Let's call it EI, right? So we had discussed that we assign, let's say, a frame here at the root joint there, and at every joint we were assigning frames, and we were assigning frame to every link, and using DH convention we were assigning these frames, and using DH parameters then we were getting the homogeneous transformation matrices, for example for link 0 with respect to the inertial frame, right? Or link 1 with respect to link 0, right? Link or joint, whatever you want to call it. But yeah, like we also talked about this, that we have to be consistent with respect to the terminology that we decide to use, right? And then we keep getting these successive transformation matrices, and then if I want the transformation of the end effector frame in inertial frame, so we know we saw that could be done using what we called composition, right, of frames. So since this is the transformation from frame 2 to frame 1, and this is from frame we should start with this, yeah, from frame 1 to frame 0, and then from 0 to frame I. So just composing them together, and the composition is done using multiplication in either rotation matrices or homogeneous transformation matrices like this. Okay, so we keep composing these. In this case it would be up till these. So this final transformation matrix will give us the relative transformation of the end effector frame in inertial frame, right? Now what does that mean, right? What does this relative transformation mean? So what we saw was that the homogeneous transformation matrix has a structure like this, right? It has a 1 cross 3 size 0 vector here, a scalar number 1 here, and this R is now, if we are calling this TEI, then this R is the relative rotation of end effector frame with respect to inertial frame, and this T here is the translation vector, right, from E to I, and this is represented in the inertial frame, right, because all these quantities are being represented in the inertial frame. And even this, if you call this matrix, so this matrix is also represented in the inertial frame. So this is what we had discussed, that if we look at this particular vector here, this translational vector, right, so this represents the displacement of end effector frame as seen from the inertial frame. It means it will give me the complete displacement starting from the origin of the inertial frame to the origin of the end effector frame. Okay, and this can also be seen from one more. This can also be verified that the if we transform the origin of end effector frame, right? So the origin as seen in end effector frame transformed using this particular matrix should give how that point looks in the inertial frame. So that was the whole concept behind using these transformation matrices. So if I want to check, right, let me call this point, let's say T. No, we are already using T. Let me call this capital E. Okay. So this the representation of this point, right, the origin of frame E in the E frame, right, in the italicized E subscript E frame, the end effector frame is this, right, because this is a zero vector. I've written transpose because this right now without transpose it's a 1 cross 3 row vector, right? We usually write vectors as column matrices, so it's a row matrix or a row vector, what do you want to call it. Now if we transform this using this matrix, what we should be able to get is representation of E in the inertial frame, right? So we essentially want to do something like this, right? And these are, we know that we just append this one here when we are working with homogeneous transformation matrices. Okay, and if I just plug in all these variables here, right, and this comes from here, right? So what I will actually get, I'll actually end up getting is just this fourth column of this matrix, right? This is a 3 cross 3 matrix, but all these values will be multiplied by zeros, so they will zero out. There will be no addition of these, right? And then there will be a 1 here, right? And this is EI and 1. So the representation of the end effector frame in, like, the position of the end effector, right, origin of the end effector frame as seen in inertial frame is given by this translational vector, right? So that was the reason why we were discussing all these preliminaries, right, to give us a method to get position of arbitrary frames as seen from other frame, right, with respect to other frames. I could even get the position of end effector as seen from frame 1, right, but in that case I would have to use the relative transformation between E and 1 and not E and I, right? So while doing all this, uh, the parameters that we use were DH parameters. So the transformation matrices, they they are constructed using the DH parameters, right? They are a function of DH parameters. And in DH parameters, most of these are usually constants. Now it depends on your joints which of these values are not constants, right? Because a joint can either rotate or expand or shrink, or whatever degree of freedom the joint allows, only those parameters will change. Okay, so this process of so for example, let's say we have revolute joints, so then theta will change. If we have slider joints, right, then only the link length will change, right, if we have a prismatic joint. So for every unique value of your joint variable, right, or the joint degree of freedom, you'll get a unique value or a unique position of your end effector, right? And this particular relation between the joint variables and the end effector, right, or the we can define end effector as any point, but usually we define it as the position of the last link or the last frame of the robot where the tool is attached. So this problem is termed as forward kinematics, and this is what you guys are is the first thing that we have learned about in this week. And this is one of the most important, like the most basic uh, equations or the most basic problems that you solve by dealing with robots, that if we change the joint variables, how does the position of interest, now we'll replace the word end effector with position or point of interest, right? We can call position of point of interest. So how does the position of the point of interest change if I change my joint variables? That is what we term as forward kinematics, right? So if I have to represent forward kinematics, right? So it's a mapping from, let's say, theta, right? We are currently only considering revolute joint, let's, for this particular case, right? So for all the given joint angles, what is the position of the end effector? And this is the vector notation, by the way, that we are using, that we introduced last time. So, right, so this underbar represents a vector, and these are the joint variables and the end effector position of a 2R robot, right? If we just draw a 2R robot, right, and this is angle theta, and these angles, uh, these were taken according to the DH convention, right? And this position of the end effector is what we'll be calling x comma y, right? So this mapping from thetas to x and y is what we call forward kinematics, right? And now of course, if we change these thetas, right, any theta 1 or theta 2 or both of them, the position of the end effector will change. And but it cannot be arbitrary, right? So this end effector, if this, let's say this length is L1 and the length of link 2 is L2, right? So the maximum distance that this end effector can go radially from this point O is just L1 plus L2, right? When the then theta 2 is 0, right? It cannot go beyond that. To go beyond that, the joint will have to break, right? And we are talking about rigid bodies that do not break. So, keeping this constraint in mind, there is only a handful of uh, positions or valid positions that this end effector can have, and if you plot out those positions, then it will give you the workspace of the robot, right? Now, depending on the length of the robot, you might have a zone here where the robot cannot reach, right? Or if both the lengths are equal, then the robot might be able to reach all the way till here, okay? And if, let's say, this L2 is very less, then this robot might only be able to move in this particular area, right? So it depends on your system parameters, on your link lengths, right? So the position cannot be arbitrary, right? But for every value of theta 1 and theta 2, there will be some value of x1. And when we say every value of theta 1 and theta 2, we want to talk about valid values of theta 1 and theta 2, right? So we say that they go from 0 to 2 pi radians, right? Because right now we are assuming that these revolute joints, they can rotate complete 360 degrees. So for every single value of theta 1 and theta 2, if you plot, right, the contour or the position of the end effector, then what you get, right, this set of points that you get is called the workspace of the robot. And this is also what you have learned this week, right? The concept of workspace of the robot. So a workspace is just a set of valid positions for the end effector, right? The end effector cannot, given the system, right? Given the system and its constraints, the end effector can only be within the workspace of the robot, right? Now, since this is a mapping, right, the forward kinematics, we can also try to invert this mapping, right? That, let's say, for a given value of x comma y, right, for a given position of end effector, what are the joint angles, right? For a given position of the end effector, what are the joint angles? And this inverse problem in robotics is called the inverse kinematics, right? So forward kinematics, inverse kinematics, and workspace. So this, I'll just give an example of a 2-hour robot and how we do forward kinematics and inverse kinematics of that, and then we can also try, plotting the workspace of that particular robot, right, for a 2-hour manipulator. So let's get into the forward kinematics. Forward kinematics for a 2-hour robot. So let us just first draw a sketch of a 2-hour robot. So we just establish that the link lengths are L1 and L2. The joint angles are theta 1 and theta 2, and the final position is what we are calling x comma y. right? So now let us start with the DH convention. So this ground frame, right, is what we call inertial frame or frame 0, right? Just E, plain E. And this first joint has the z axis or the axis of rotation perpendicular to this plane, right? So my z1 will coincide with z0, right? If I call this x0 and y0, right, the basis vectors of the inertial frame, then z0 will be perpendicular to the plane of paper and z1 will coincide with z0. And similarly for z2 at second joint, right, it will be out of the plane of the paper. And we discussed last time that we also assign one frame at the end effector, right, because we want to write the position or an orientation of the end effector. So we call this z3. Now to attach the other axis, right, we know that it is the common perpendicular of the consecutive joint axes. So in this case it is along the link, right, along link 1 it is x1 and along link 2 is x2, and as we discussed earlier, we keep the orientation of the end effector frame same as the orientation of the last frame, right, the frame just before that. So x3 we are aligning with x2, and for y-axis we just need to take a cross product, right, because we are using right-handed coordinate system, right? So we know that all of them follow the cross product rule. So z cross x will give us the direction of y, right? So since z is out of the plane and x is along the link, so if we do z cross x, right, we get the position of y as being perpendicular to x1 but rotated from y0 by an angle of theta, right? Makes sense also. Similarly we do for frame 2 and then frame 3. Frame 3 here is our end effector frame, right? So now what we can do here is get the transformation matrix from frame 1 to frame 0, frame 2 to frame 1, frame 3 to frame 2, and then multiply all of them to get transformation from frame 3, that is the end effector frame, to frame 0, right? And then as we had discussed just in on the last page, we transform the origin of the end effector frame using this homogeneous transformation matrix, right? Or we can also say that the translation part of this homogeneous transformation matrix will give us the position of end effector in the inertial frame. Okay, so let us try to find these matrices, right? Now just a quick disclaimer, we can very quickly using geometry find out the position of the end effector for this 2D case, right? It's much easier that way, but why we are going through this procedure is because this is a general method, right, to get the position for any arbitrary system. When the system is not 2D or not very straightforward, then using intuition or geometry might be a bit difficult, but when we have a set method, then we can just write an algorithm, use a computer and just feed it, let's say, the origin of the end effector and let it do the multiplication, all that. So the hard part, we just figure it out how to do that, and then we program a computer to do it for us. We don't do it ourselves. So this way is more general, but of course, it's a bit more tedious to do by hand. So by geometry, we can see that the x position, right, of the end effector is actually L1 cos theta 1 plus L2 cos theta 1 plus theta 2, right? Because this angle is theta 1 right here, and this length is L1 cos theta 1, and this length here is L2 cos this whole angle theta 1 plus theta 2, right? So this is the x, and y, similarly, we can, if you just apply geometry and take projections, right? So because y is now just the sum of this projection and this projection, right? So this is the position of the end effector, right? So this is what we were after actually. This is our forward kinematics, right? But what we are going to do is we are going to arrive at this using the method that we have already learned, right? Again, we could do this easily for this particular case, right? But this requires a lot of intuition, and that might not be the case for many problems, right? It might not be so straightforward. So let's start with our first transformations between frame 1 and 0, right? So for this we need rotation matrices and the translation, right? These are always constant, right? These four terms are always constant. So rotation between 1 and 0, right? Rotation matrix is the rotation about z, right? Now what is the rotation, or what are the rotations that you need to do to go from frame 0 to frame 1, right? So you just need to do one fundamental rotation about z by an angle theta 1. And last time we saw what is the expression for these fundamental rotation matrices, right? That is, like for z, this is the fundamental rotation matrix, right? And now what is the translation, right? What is the translation vector between frame 1 and 0, right? So that is actually just zeros, right? A bunch of like 3 zeros, because both of their origins are coincident, and both of these quantities are being represented in frame 0, right? This is important. So if we try to write t10, then we will end up with sine theta 1 0 1 0 0 0 1. Good. Now if we, now this, here we have our t10. Now we could also arrive at this using the DH convention, right? We could write DH table, then we could use the relation that we already have, right, between frame I and I minus 1 in terms of DH parameters. That is one way to do this, and like that we arrived at, like the expression for this consecutive transformation matrix, homogeneous transformation matrix, we did arrive at, and we saw the logic or the or what were the steps that were followed in the derivation for us. So we just did the same steps, but we went through that procedure because we knew that it would be easier this way, right? There's only one rotation involved. Similarly, if we want to write for t21, right, then we need r21, and we need T21, right? We need these two things. So rotation, relative rotation between frame 2 and 1, right? That is again just a rotation by theta 2, right? Not theta 1 plus theta 2, because now we are just doing between 1 and 2, and between 1 and 2 there was only one rotation, right? Theta 2. If we look at in the diagram, between 1 and 2, right, between x2 and x1, we only have theta 2. So now I'll start using the shorthand notation for cos and sine, so that it's easier to write, right? It does not clutter the space. Now, what is the translation, right? This translation vector between frame 2 and 1. And again, it is in frame 1 this time, right? So if we see that the origin of frame 2, is at a length L1 apart along the x1 direction, and there is nothing along y1 or z1, right? So it is L1 along x and zeros along the rest. So if we just plug everything in here, then what we get is the homogeneous transformation matrix for frame 2 to 1, right? And now if we do a similar procedure to get from 3 to, now if you were paying attention, then we mentioned that we purposefully kept the orientation of frame 3 and frame 2 similar, right? It means the relative rotation between them is identity, right? There is no rotation. So identity rotation is represented using an identity matrix. And if we want to know the displacement, right? So it is L2 along x2, right? Nothing along y2 or z2. So L2 0 0. So now we have here our the transformation matrices that we required. Now what we need to do is we need to get the final transformation matrix, final homogeneous transformation matrix between frame 3 and 0. For that we need to compose these three. By compose we mean multiply. So that is what we are going to do. So T3 0 is T1 0 multiply T2 1 multiply T3 2. Right? So now it is just a matter of algebra. So I'm going to do that a bit fast. I'll try to do that because this you can like work it out on your own. Because now we are just going to do matrix multiplication basically. Because that is what we're left with, right? A bunch of matrices in some particular frames that we now want to multiply. So let us just write this as it is and multiply these two first. Okay. So since this part is identity, it won't change anything here. Right now for the translation part, it will be L2 C2 here plus L1 and L2 S2 and 0. now we multiply these two. These are like separate columns. And this will be our L1 C1 plus L2 C2 C1 minus L2 S1 S2, right? And then we'll have L1 S1 plus L2 C2 S1 plus L2 S2 C1. So this is the final homogeneous transformation matrix between frame 3 and 0, right? Now if we just look at them and try to simplify it, then we'll see that we can use some of the trigonometric identities here, right? So this particular identity is for cos theta 1 plus theta 2, right? So I will write it as C12, right? So if I have to define C12, I will be writing for cos theta 1 plus theta 2. And similarly here it is minus sine of theta 1 plus theta 2. S12, C12, zero, zero, here, 1. And similarly here also, we are seeing cos of theta 1 plus theta 2, right, multiplied with L2. So this is L1 C1 plus L2 C12, and here sin theta 1 plus theta 2. S12, 0, 1. So now you see, if you compare it with our geometric solution of the position of the end effector, right? So the x and y are actually matching the x position, y and y position, right? The first two components of the translation vector are matching our x and y position, and that is also what we had claimed before, that the translation part of the homogeneous transformation matrix gives the position of the origin of the you can say target frame into the required reference frame. Right? We can also like try to multiply the origin, then we'll be only left with this. But what we have established here is that the x and y position for a 2R manipulator are these, right? And what is z? Z is 0. We can see that here. Now this matrix here, this rotation matrix, okay, this is the orientation of your end effector frame with respect to your inertial frame. Okay, so if we want orientation information, we look at the rotation matrix part, and if you want the translation information or the position information, then we look at the translation part, right? So this is the advantage of using the homogeneous transformation matrix, is that it gives us the information about the complete pose of the object. So the information about position as well as orientation. Now this is the forward kinematics solution for 2R. Right? But now what if we want to find the inverse mapping for this case, right? We currently we had assumed that we know theta 1 and theta 2, then we were calculating the values of x and y. Now what if we know the values of x and y, but we want to calculate the values of theta 1 and theta 2, right? So that is the inverse kinematics, right? That is the inverse mapping of this. Now there are multiple methods to do an inverse mapping, to get inverse kinematics for a robot, right? So the first one is the analytical solution. Like the two very broad classes of solutions is analytical and numerical, right? How numerical? Because you see, this particular equation, it has, there are two equations and there are two variables that we need to find, right? Theta 1 and theta 2. So you can actually try to apply a Gauss-Newton approach for root finding for this particular case, right? For this particular equation. So that is the numerical method. But what we are going to look at is the analytical method, right? Because if we have a closed form solution for the values of theta 1 and theta 2, that can be much faster to calculate, right? We don't need to do multiple iterations. We can have answer in a single in a single iteration, right? Single attempt. Numerical methods, they are almost always iterative, right? So they take multiple attempts, they take multiple guesses to reach the right solution. So one of the ways of solving these system of equations analytically is the elimination method. Right? So since we have two variables here, we will try to arrange these equations in such a way that eliminates either one of the two variables, right? So since we can see that there are causes here and there are same sign, like corresponding signs, right? Cos 1, cos theta 1, sin theta 1, cos theta 1 plus theta 2 and sin theta 1 plus theta 2 multiplied with the same constants, right? So what we could actually do we could actually try to do to eliminate any one of those is to try to square and add these. So if we write x square and y square, it will actually come out to be, right, because L1 squared C1 square plus L1 square S1 square will just become L1 square plus 2 L1 L2, the multiplication of this plus the multiplication of this, C1 C12 plus S1 S12. Now these trigonometric terms here, they become the expansion of cos A minus B, right? So this becomes cos theta 1 plus theta 2 from this minus theta from this. And here we see that theta 1 gets eliminated. Right? So what we are left with is just an equation with theta 2. So now we can invert this, like we can rearrange this whole equation to get the value of theta 2, right? So cos theta 2 is y square minus L1 square minus L2 square divided by 2 L1 L2. Now it might be tempting to just take the cos inverse of this particular value and call it a day, right? And call that as the value of theta 2. But as we know that cos theta and cos minus theta have the same value, so you will only get a solution in 0 to pi if we do cosine inverse, right? So rather than this just jumping on doing the cosine inverse here, what we are going to do is we are going to look the reason for multiple solutions, right? Because as I said, since it is a single value, so there must be two solutions for theta 2. One will be, let's say, plus theta 2 and other will be minus theta 2. And when do we choose which, right? What does this mean? Which one are we allowed to take? So let me just write this here again, right? Cos theta 2 is x square y square. So what we do is we try to write sin theta 2, right? And what is actually sin theta 2? It is square root of 1 minus cos square theta 2, right? We just use the identity of sin square theta plus cos square theta equal to 1. But we should add these two symbols here, right? There is not just one solution for sin theta, there are two solutions, plus and minus of square root of 1 minus cos square theta. Now, which of these two solutions should we choose, right? And what do these two solutions actually represent, right? What, because we knew, as I told, that if we just take cos inverse, then it will just give me a value between 0 and pi. So what it actually means is that, say this is our origin and this is the position of the end effector, right? There are two ways in which there are two configurations of the robots that lead to the same position of the end effector, right? One is called the elbow down configuration and the other is called the elbow up configuration. These are just the terminologies that we use. But we can see here clearly that there are two possible solutions and that is being reflected here. Right? There are two possible values of theta 2. This particular thing is called branching of solutions. Right? So there are multiple branches of solutions, there are multiple solutions, and now we have to choose one. So if we choose plus 1 here, right? If we choose sin theta 2 to be equal to plus or positive of square root of 1 minus cos square theta 2, it means that we are choosing this particular branch, right? This corresponds to plus theta 2. And if we choose minus of square root of 1 minus cos square theta 2, it means that we are choosing this branch. Right? It means we are choosing the elbow up configuration. So now we see that using both of these does actually give us the complete solution of the problem. Right? So how we finally calculate theta 2 is actually we do tan inverse of these two, right? And we do not use, so in computer there is an a tan function and then there is an a tan 2 function, right? A tan function suffers from the same problem as cos inverse, is that it does not give the solution in the complete range from 0 to 2 pi, right? Because it cannot distinguish between the numerator and denominator being both positive or both being negative, right? It treats these as the same, right? So this one also gives solution only from 0 to pi. So there is a function called a tan 2, and that is what we always use while programming, because this one actually preserves the sign of numerator and denominator, and it returns the solution in either minus pi to pi or 0 to 2 pi, based on what we choose, right? So this is actually the final value of theta 2, right? And again, cos theta 2 is calculated only from the values that we know, x, y, L1, L2, right? And the sin theta 2 is calculated from cos theta 2 and our choice of the branch, right? Which branch of which elbow up or elbow down configuration we want. Now, once we have theta 2, right, we consider it as a given, because now we have calculated the value of theta 2 and we use this to find the value of theta 1, right, in the elimination based method. So we are essentially plugging the value of theta 2 in the earlier equations to get the value of theta 1. So it is L1 C1 plus L2 C12. So what it means that we are treating theta 2 as a given is that now our theta 1 can actually depend on x, y, L1, L2 and theta 2, right? Our theta 2 could only have depended on these quantities, right? X, y, L1, L2, because these were the given. But once we have theta 2 as well, we use that also to represent theta 1. Okay? So now also we do certain operations here to isolate theta 1, right? Because here theta 1 and theta 2, they are coupled, and we want to isolate theta 1 so that we can get a closed form expression for theta 1. To do that, what we do is we open this using the identity C1 C2 minus L2 S1 S2. Similarly for y. Now what we'll do is we will gather the terms for C1 in one side and S1 in the other side. Now, since these quantities are already known, right, because C2, theta 2 is also already known, as we have already discussed. So we will just, replace these quantities with some smaller, easier to handle variables. we, let's say, call this k1, and we call this particular thing k2. So this becomes k1 c1 minus k2 s1 x, and y is k1 s1 plus k2 c1. Now what we'll do is, since now these k1 and k2, they are two numbers, right? So they are two independent numbers, so they can be represented by any 2D representation. So what we do is we choose a spherical 2D spherical polar representation for k1 and k2, right? So we just replace it as let's say, instead of k1 and k2, we replace them with r and phi, right? And this becomes r sin phi. Okay, so r c phi, r sin phi, the representation that we were already using. Okay, so this becomes r c phi c1 minus r s phi s1, and y becomes r c phi s1 plus r s phi c1. Okay, and now this becomes c, we can just write cos of phi plus theta 1, and this becomes sine of phi plus theta 1. Okay, now you see we have both the sine and the cos here, right? So I can take tan inverse directly using both the values, because we have both the sine and the cos, right? So we won't have the problem of getting only a partial solution. We will get a full solution if we have both the sine and cos. So phi plus theta 1 is actually tan inverse of this y over r comma x over r. But we want the value of theta, right? Minus phi. And what this actually is, okay, if we want to know what phi is, right, we can apply the same rule here. Since we know the values of k1 and k2, right, and r essentially is just square root of k1 square plus k2 square, right, because this is the polar distance of these two coordinates. So we can apply the same tan inverse for these k2 over r comma k1 comma r. Now this is we should write this. This is the final expression for theta 1 for the 2R manipulator, right? So now we have done both the forward kinematics, right, in which we have seen that through geometry as well, that the coordinates were these and z was 0, and given x and y, we also calculated theta 2 and theta 1, but there was an order here that we followed. We first calculated theta 2, theta 2 comma c theta 2, where c theta 2 was x square plus y square minus l1 square minus l2 square by 2l1 l2, and as theta 2 was a choice of plus and minus square root of c theta 2 square. And then given theta 2, we wrote theta 1 like this. Right? Now clearly, if you see that the choice of sine theta that you make here, like the branch that you choose will change the value of theta 2, which in turn will change the value of theta 1. And that should actually happen, right? Because if we choose this branch for the solution, then your theta 1 is the smaller one, this angle here, right? But if you choose this branch, right, then your theta 2 is this one, and your theta 1 is this bigger angle. So theta 1 will change depending on which branch you choose, right? Because there are two different solutions for the same point, right? So we just had to make a choice which solution we want. So this is mostly what is covered in the assignments also for this particular week, and I think this should be more than enough to make you understand the concepts as well as how to apply these for at least the 2-hour manipulator, and you can extend this same principle, same method to any non-redundant and non-under-actuated robot, right? Only the fully actuated robot. For example, a spatial 3 degree of freedom robot, you can handle using this. Even 6 degree of freedom robots, so we'll discuss in class, they can be handled using this method of elimination, right? So this method that I have outlined here is actually a really powerful method to get the inverse kinematics of the robot. But if we do not want to go this way, then of course we always have the numerical methods, right? We just pose this as a root finding problem and apply any of the algorithms that we want, for example Newton's method, and we might get a solution. Why I say might is because sometimes when your relation is not so straightforward, you might get stuck in a local minima, and in this particular case we saw that there are two different solutions, right? So how do we, so there are basically two distinct routes, right? There are two possible sets of solution. So if you use a numerical method, which solution will we end up in? That either we don't know, or we have to take that into account as well while going for a numerical solution. So I think this is enough for this week, and I will upload this lecture on the YouTube. Maybe the link will be it's already shared with you. So okay, yeah, bye. I'll end the meeting now.